This is Yogyakarta. Down there in those dense grids of streets and neighborhoods, more than 3.5 million people go about their daily lives. But looming over it all is Mount Merapi. It is Indonesia's most active stratovolcano, a constant, smoking fixture on the city's northern horizon. Merapi does not erupt randomly. It operates on a ruthless, measured rhythm. Heat and pressure build in a continuous cycle, turning the mountain into a massive geological clock. This timeline visualization maps that cycle. Minor eruptions, classified as 1s or 2s on the Volcanic Explosivity Index, happen roughly every 1 to 5 years. Larger VEI-3 events hit every few decades, and about once a century, the pressure triggers a catastrophic VEI-4 eruption. Because the cycle is continuous, the pressure is always building. The scientific challenge isn't stopping the eruption. It's reading the internal mechanics of the volcano to know exactly when the clock will strike zero, so everyone can get out of the way. To read those mechanics, researchers from the Merapi project mapped the physical structure beneath the mountain. A sub-vertical plumbing system channels magma continuously from the deep moho layer, 20 kilometers below sea level, straight up into a shallow reservoir. That relentless pressure forces magma to the surface, rapidly inflating the summit, creating highly unstable lava domes. Eventually, the dome grows too heavy. Gravity takes over and the structure fractures, sending avalanches of fragmented rock and 1,000-degree gas tearing down the slopes. These are pyroclastic flows. Scientists call them awan panas guguran. Locals refer to the terrifying billowing clouds as wedus gembel. Because the deep plumbing system constantly pushes magma upward, these catastrophic dome collapses aren't anomalies. They are a mathematical certainty. To track exactly where the mountain is in that cycle, the monitoring agency listens to the geological tension inside the rock. The first indicators are acoustic. Seismographs detect a sharp increase in multi-phase quakes and high-frequency vibrations. As the magma forces its way up through the rock, it creates a distinct seismic signature. But sound is only half the equation. The agency also measures physical strain using electronic distance measurement. This visualization shows the EDM data in action. As the internal reservoir fills, the pressure physically pushes the volcano's flanks apart. The mountain literally swells, bulging outward by several centimeters a day as it reaches a critical threshold. When the high-frequency quakes align with rapid physical expansion, researchers have a measurable countdown. The rock is stretching. Structural failure is imminent. We can see proof of these immense underground pressures by looking at the aftermath of an eruption. The material that rains down on the surrounding villages is a direct record of the internal mechanics. This chart displays an XRD pattern breaking down the mineral composition of Merapi's ash. The peaks here indicate heavy concentrations of plagioclase feldspar and a silica content reaching up to 61%. Under a microscope, that material forms jagged, fibrous glass particles. Intense heat and dissolved gases create tiny cavities locked right into the ash. High silica content makes magma thick and sluggish. Instead of flowing smoothly, it clogs the plumbing system, trapping the dissolved gases until the pressure violently shatters the rock. The chemical makeup of the ash provides a forensic record. It confirms the massive summit explosions are dictated by specific chemical reactions happening deep underground. All of this data, the deep seismic rumblings, the daily expansion of the dome, the chemical analysis, is ultimately used by the BPPTKG to set survival protocols for the population below. The agency maintains a strict 4-tier alert system, updating the public as the volcano cycles from baseline activity up to an imminent explosive threat. This map shows what happens at level 3. Authorities trigger immediate evacuations, creating an exclusion zone stretching 3 to 7 kilometers from the summit. They specifically target communities along the Babang and Kresak river drainages. Those valleys act as the path of least resistance for pyroclastic flows. When the dome collapses, the 1,000-degree gas and rock funnel directly down these channels, instantly incinerating anything in their path. By quantifying the exact physical state of the volcano, this alert system translates raw geological data into mass evacuations, pulling thousands of people out of the path of the flows just in time. Because of its frequent, predictable cycles, Merapi serves as a vital laboratory. It provides one of the clearest windows into how subduction zone volcanoes operate. The high-resolution models of magma transfer and structural deformation built here are exported to observation posts around the world, helping agencies recognize exact pre-eruptive signals in other restless mountains. Understanding the rhythmic mechanics of a volcano will never allow us to stop the eruption, but it does buy humanity the one resource we need most to survive it: time. Thanks for watching TEMBODocs. If you found this breakdown of Merapi's geology helpful, please like, subscribe, and let us know in the comments which geological process we should investigate next.